Okay, so today we have a lot to cover, unfortunately. As I kept promising, we're going to learn Vhdl, which is something that wasn't done very well, I guess, in previous courses. So this might be less of a review for some of you and more of new material. But to make sure everyone is in the same place, we're going to start with some of the background, essentially. So way back in the long ago, let's call it the 60s, you had a couple of different technologies, and they were starting to refer to them as small-scale integration, and that's when you have 10 to 20 devices that you hook together, and you would use K-maps and other techniques in order to simplify these. Then it went to medium-scale, large-scale, and ultimately what we have now, which is VLSI, very large-scale integration, right? And this is when you have 100,000 or more devices, or 10,000 or more devices. I don't remember what their exact cutoff is. There is an idea of ultra-large scale integration, ULSI, but VLSI has become just the name for anything that is very large. So at this stage in real digital design, gate level and flip-flop level design, kind of what we reviewed in the early, is pretty rare to actually go through all of that work, because you can use hardware description languages that can be compiled into hardware. So you only need to know how to program. You don't necessarily need to know the gates. However, you do need to understand the gates in order to avoid what we call synthesis errors, which is when you take the code and then turn it into hardware. And a lot of what you're going to learn is how to avoid that kind of problem. So the idea of programming language to hardware we call computer-aided design, right? CAD. And when we use computer-aided design, we want to use some sort of design flow. And you're starting to get fancy names that take in the whole project management level, right? One of the big ones right now is Agile. And that's largely used in software, but you'll probably run into it as hardware, and we may end up covering a section on that. But for right now, we're going to stick with the good old-fashioned how they used to do it, essentially. And the first thing, imagine you're a hardware engineer, right? The first thing that happens is a customer comes to you and says, I need a system to do this. So that's what we're going to call your requirements, right? So you get your system requirements. You're like, okay, how do we take those requirements and actually do something with them? And then you're going to move on to I'm just going to write design specifications. And that is essentially a translation of customer desire into physical constraints, right? So it might be, okay, we're going to need a radiation hard FPGA that has at least 10,000 devices on it, and anything coming in, the ADCs need a resolution of 12 bits on it, and so on and so forth. That's your design specification. Once you have that design specification, design formulation. This is really the meat and potatoes of how you're going to do it. And for us in this class, that pretty much means VHDL modules, but a lot of times designers will start, myself included, with block diagrams, right? Like, I'm going to know that I need some controller, and it's going to feed out into some output module, and so on and so forth. And I'll draw out the tree of what that system is going to look like. And what's nice is once you have this, once you finish a block diagram, you can just start throwing VHDL code into that. So your block diagram is this conceptual level how are we going to put this thing together, and then the VHDL comes later when you actually just implement it. What we call this, the VHDL that you're plugging into it, is the design, I'm just going to do some ticks, entry. Right, so top level, throw some VHDL in, we call that design entry. In the case of VHDL, after we do that, we can simulate it. Vhdl, which we installed in the lab, has the ability to do very robust simulations. And in the case of VHDL also, we call simulations, we set up the simulations rather, using a term called a test bench. After you've simulated it, you can turn it into logic. So we skipped this step in the lab, right? We didn't simulate anything, but we did go on to synthesis. And that was as easy, in our case, as clicking a button, which took the code that we copied and started figuring out how to turn that into hardware. You'll also see this with the full term is logic synthesis. I almost always will just say synthesis. You'll then move on to, maybe not, into post-synthesis simulation. And what this does is it goes, okay, I've used these devices and formulated this hardware, and now I'm going to use physics math to run the simulation. So rather than just logic progression, it is actually trying to simulate the results using the real devices. And that gets more accurate and is really important in like high-speed design. But there's going to be other issues that we'll get into when you're actually coding that will explain why that matters. Sorry, it's getting a little low. You'll then move on to map, place, and route, right? And what that means is taking the logic that is formulated and actually putting it on the device. So figuring out where it goes on the device, placing it on the device, and then routing the connections together. Then you'll either, from here, you might put this on an FPGA, right? That's what we did. There's also the possibility of putting this on what we call an ASIC, which is an application-specific integrated circuit. So there are some benefits to each of these, and essentially FPGAs, still programmable. I can go out and I can just change it whenever I want, right? All it takes is plugging in the USB, clicking run, and I can update the code. ASICs tend to be more robust. They tend to be faster. They tend to be better signal integrity, smaller, because in an FPGA you have a bunch of extra logic gates that you didn't use. An ASIC is only the result of the logic gate that you did use. So it can be much smaller, and a few other benefits. And it is important at all steps. So I draw arrows like so from like here, that I might go back to design specs, right? I may get somewhere and go, this isn't going to work. And I might have to come back to design specs, or I might come back to design formulation. Your book has a diagram, and I think they put the arrow into this transition, which has the implication that they're not going back to the design specifications, which is a little bit weird. So we'll stick with that for the exam, that kind of arrow, because that's what's in your book. The reality is you will frequently see going back to the design specification stage in order to make changes. But your book will have this type of diagram. So, if you ever go to grad school, you'll see plots like this all the time that they really like to do. Let's see, what do they call this? Where you're going to have some sort of trade-off, right? So the purpose of like grad school is research, and you're actually going to run into this kind of concept at an industry as well, where you're going to have this plot of the cost, design time, and speed on one axis versus density and customization. So if you take discrete components, so you take like just a logic gate and you start building them with discrete components, it is not dense, but it is really, really cheap. PLAs, PLCs, these types of things, those are, I refer to them as baby FPGAs. You'll see a lot of those in industry, in like automation and large machinery, because they only need a little bit of logic, and so they're pretty cheap, they're pretty customizable, but they're limited by gate size, really. And then they have CPLDs, which the C is just complex. That's all that is. And then FPGAs, this is where a lot of what you'll work on in industry if you go into digital design is, because FPGAs are very versatile, still fairly cheap, and you can make them quickly. The turnaround and editing and changing is very quick. ASICs are very expensive, very complicated to make, require quite a bit of education just to get to that point. But they're the most customizable and the best performance at the end. Yeah?
Question, where does Arduino and Raspberry Pi kind of fall in this? Or do they? Are they just another?
So on this particular one, they're a little bit off, not on this scale, because while they are made out of digital logic, they are more complex. So what you're actually going to do for these labs is you're going to take an FPGA code. I don't know if we're actually going to throw it on an FPGA yet, but you're going to design, using at least simulation, code for a microcontroller, which is what an Arduino is, right? So it's some level of processor. So you're going to design that, and you're going to make it, and we're going to design code that could be, at the very least, put onto an FPGA. Now, what you're going to be doing is a very simple 8-bit, we call it MIPS, M-I-P-S, and it's not that hard, right? And it's just a series of instructions, and you'll tell it what to do and add. It'll do like math operations and such. Arduinos are obviously more complicated than that, but you could, with a sufficiently complex FPGA, put a whole Arduino onto it. It would just need to be big enough. So that's kind of where they fall, is microcontrollers are a specific implementation of digital logic, and an Arduino is an ASIC. That's all it is. It is an application-specific integrated circuit that has been designed to be a processor, and you will kind of, by the end of this class, you'll somewhat understand what they did to get there. Okay, any other questions? Good. Okay, so like I've mentioned before, we're going to use VHDL. HDL is hardware description language, so it's a language that is designed to describe hardware. You can break this down into two main categories. If I ever spell something wrong, let me know. I've become, too reliant on spell check. So behavioral is what it sounds like. You're describing the behavior of it using a hardware description language. Structure is you're describing the structure of it. So behavior is going to include things like mathematical expressions for logic, whereas structure is going to be used for, like, I want this gate connected to this gate in this particular way, right? This and that and this, so on and so forth. Most of what we write is in behavioral. So when we have a block diagram like this, so they have some sort of control system going on with some outputs. These are just like LEDs or something, right? They're just lights. You're going to write each of these modules separately, usually in behavioral, and then you're going to write some structural to tell them how to connect these together. That's generally how we structure VHDL, which is pretty convenient for debugging later. Yeah, so we'll go through some examples, I think, in a bit of like an adder. So you could have something that adds things together, and you could easily describe that as the mathematical expression of adding or as the gates that are an adder, because it's really not a complicated circuit. In the text, there's a section in there that goes over like the history of VHDL. I'm not going to cover that today because although it's kind of interesting, it's not worth our time in class, let's say that. But because this is the structure of VHDL, you get behavioral models tied together with structural, VHDL really lends itself towards what we call top-down design, which is where you start with these block diagrams and then you design inwards, essentially building more and more specific blocks as you go. There are other languages, of course, for hardware description. There's Verilog. Someone's made a Python that is meant for hardware, and there's also a C# version now, I believe. And I think there's 2 or 3 others that have been used. Okay, so we have VHDL. We're aware of the background. Let's build a circuit in VHDL. It's pleasantly easy. Let's see, D and E. So there is the ability to write C. We're going to start C, right? We're going to start with some assignment. We use this for the equal sign, and there's a reason for that, which we'll get to a bit. Is A and B. Now, this next notation, your book is really big on this. It bothers me a little bit. So this is what C is. C is A and B after 5 nanoseconds. Anyone tell me what this after 5 nanoseconds is for? The delay from the gate. The propagation delay is the term that we want to use. And then we're going to have E, same little equal. What's it going to be? Yep, C, or D after 5 nanoseconds. So I've said this before, I believe. I know I said it. I have 2 of these classes. Sometimes I get confused. I've learned on Verilog. Now, I've started spending time, starting this summer in July, with Vhdl learning it so I can teach you. And as far as I can tell, to the best of my ability, is Vhdl, much like Verilog, has no ability to synthesize this statement. So if it can't synthesize this, why do we put it in?
So we know.
Close. It's actually so the simulator knows. Because otherwise it doesn't, pre-synthesis simulation doesn't know that there's a propagation delay, right? And so they'll introduce this term, delta, where it will happen after a short amount of time, which is as short as the simulator will make it, essentially. So if you don't write after 5 nanoseconds, it really is assuming after delta. That's default there. So you don't have to write that. You will get that. This will matter for some types of circuits, right? The most obvious one is if you just have this as an inverter, right? A 1 goes here, that means it zeroes out, but then the 0 feeds back around and makes it a 1. So this is going to create an oscillator. And if you write after 5 nanoseconds, that's going to give me what output, right? It's going to go 0, 1, 0, 1. Oh, look, I've made a clock, right? And in simulation, it's going to look like a pretty good clock because I've said after 5 nanoseconds. If I don't say after 5 nanoseconds, it's going to even worse than I can draw, right? It's just going to be a constant blur of up and down. And because it uses single data points, it's actually going to probably look like a squished together sawtooth like that. So trying to get the propagation delay can matter. And we actually do use circuits similar to this. They're a little bit more complicated to make sure the timing makes sense, but we actually do use similar circuits like this in PLLs, which is how you generate clocks. Okay. Now, there's a difference between VHDL and like C or Python. So who here knows Python? Who knows C? Okay, so each of those, if I wrote these lines of code, right, this happens and then this happens. Most of the time in VHDL, I'm going to have a begin and an end, and these will happen at the same time. These are what we call concurrent statements. And you can have a whole bunch of them and they will all happen at the same time. Now, if you don't have a specific clock on them, which we'll go into how to clock later, when these happen is any time any of the input variables change. So, one second. This is what we would call an asynchronous design, meaning it's not clocked. It's just going to react to inputs changing. So if A, B, or D changes, it's going to update the output. To implement something, I erased it. Something like this, right? A really simple is I could have a signal that I call clock. And I could say is equal to not clock after 5 nanoseconds, right? That's basically all that is. It will implement that if I synthesize it, but it's not going to actually have a 5 nanosecond delay. It can't make that gate have exactly a 5 nanosecond delay. There's going to be an issue, which is why the after is not synthesizable. The other one that is weird is for your operators. They are not case sensitive. So not is equal to not. When you write VHDL, it's on a laptop or on your computer, whatever. It's usually very easy. It's a good idea to use the capitalized version because then it stands out. I'm going to skip over this to make sure I get everything covered. There's another example in the book that goes through I'll draw up the design so you have an idea. Right, and then there's going to be a statement for each of these. D is equal to, E is equal to, F is equal to, and then it's going to go through that it will execute after some amount of time. And in the book example, it uses D equals this after 2 nanoseconds, and E is equal to that after 1 nanosecond, and F is equal to its equation after 3 nanoseconds. So it's showing a different one. It does a poor job of explaining it's not synthesized that way. Okay. Let's get into some more of the nitty-gritty bits. So, does everyone know what I mean if I'm talking about a vector or a bit array, right? You can talk about the same thing. So if you have B is assigned to 1100, and you write that statement, I think it needs those. Then we're going to have an array this and doing that is roughly the same, right? I'm just putting all of those into B, which is a bit array. You can also, so you can't, oh, sorry, you need these. Similarly, if you had an A and a B, and A was also 4 bits, you could do something like and they all technically end with semicolons. I'm going to forget to write those a lot. Where C is going to be a 4-bit vector of the ANDed A and B. Yeah.
So if C was just 1 bit, you'd get an error, right? You're trying to show 4 bits.
Yes, so if you had previously defined C as a 4-bit, and then you tried to throw 4 bits into it, in VHDL that would cause an error because it is what we call strongly typed, meaning it will not do any automatic adjustments of the type for you. If you ever switch to Verilog, Verilog is very weakly typed, and it will try and guess what you're trying to do, and it will cram that down into 1. So you can see how VHDL is a little bit harder to program, but it's not going to let you get away with these mistakes that may surprise you down the line somewhere. Okay, so that's the basic structure of really simple code for VHDL. But when we want to start putting this together into what we call modules, that's what a block is going to be. And you can put a module and a module and a module. And we start with an entity declaration. And so if we call an entity 2 gates is, I always laugh a little bit at VHDL because they really like this. So entity 2 gates is, and then you're going to assign port to it, which is really just your inputs and outputs, right? That's what a port is on a computer, is an input or an output. And then we're going to say it has ports A, B, D, and these are in bits. And we're going to have an E that is an out bit. And then we can end the entity. So this is where we start to make a module. Now you'll notice this doesn't tell us anything about what it does, but it does tell us what ports are going to exist and not only are they in or an out, but also what type they are. So these are going to be bits, right? And this is the same and OR gate that we're going to build up that I drew on the board earlier. Then this needs an architecture. So then they say, well, let me finish writing this. Now we're saying it has an architecture. We're going to call that architecture gates. That belongs to, so of 2 gates is, and then we're going to simply define it. But before we go into writing the logic expressions, I know there's going to be an issue because internal to it, there is a signal C, right? And that is a bit. My semicolons look like J's, and I'd really like to apologize for that. So you have architecture. You're defining the signal bit because it's not one of the ports. So anything that isn't one of the ports needs to be defined inside the architecture. Yeah?
Can you explain one more time what is the in bit and the out bit?
Say that again?
The in bit and the out bit right there.
Yeah, so this is the structure that we're going to build up. This is where my module is.
Yeah, I got it.
And then my bit A, B, and D are all input bits, and E is an output bit. So when I have a black box in my system, I can then go and change this and just draw a block like that. So you may be, down the line someday, a systems engineer. And all you're going to ever do is you're going to start drawing blocks like this, where you're going to say, I know I need an ABD and an input and an E output, and then you're going to draw these diagrams and hand it to someone, and then they'll start by going, okay, I know it needs to look like this, and then they'll start actually building the logic. Make sense? Okay. So now, we're at the point where we're going to write begin and end. So that's the architecture, right? So back to this simple coding. I didn't write the after 5 nanoseconds in this. Oh, I have a note to myself. I'm going to take the photo of the classroom as roll for my COVID requirements. Exactly right. Yeah, I'll recognize you all by your eyes.
Dr. Gardner,
Yeah,
are we allowed to use in-out?
you are allowed to use in-out. That is, so there is a third type that is in-out that I'm not going to address in today's lecture,
Okay.
but it does exist. There are actually another type called buffer. I've yet to use that one, actually.
So would it be like advantageous to use C as an in-out, or is that just weird?
Not really, because it's not going out or in of the module, so it's best off left as signal. You can also define, I hate doing this, in a port map, I could write port AB in integer, so that's a recognized type, it's allowed in Vhdl, colon equals 2. So what that's going to do is it's going to initialize the value to 2. However, again, not synthesizable. It works in the simulation, it does not make that true when you make the logic. Everyone got that? Yeah, so here's my note saying we generally restrict ourselves to in, out, and in-out modes, and mostly in and out. But, here's the architecture.
So, do you need semicolons after the word map thing, or after the
So after the entity, no. After end entity, yes. After port, I believe yes. Let me double check that one. Yes.
What about begin and end?
I don't
You need us at end.
think you need it on begin.
You need us at end.
I do need it at the end for sure. I just don't think I need it on begin. So, not begin, yes, end. There is another weird thing that you can do. It's not that weird. Where it's sometimes useful for readability to put your ins on one line and your outs on another line, or even all of your each on its own line. So you write A in integer, B in integer, etc. But we're going to do just this as ins and outs on their separate lines. So I could have C out. And in that case, it actually still does need the semicolon at the end of the first line, even though the parentheses doesn't come until later.
Well, because we have
Sorry, I can't really hear you if you're asking a question.
Okay.
What's fun is yeah.
So I have a question. I can't remember in VHDL. So say that A is an 8-bit binary number,
Yeah.
and B is a 4-bit binary number. Can it perform basic mathematics like addition by taking the lowest 4 bits of the 8-bit number and adding it with the other 4-bit number, or does it not do that in VHDL? Because I can't remember.
If you're trying to add I think that's what you're asking. If you're trying to add a 6-bit number to, say, a 4-bit number.
Right. Does it just give you an error, or does it actually?
Yeah, so it wants you to give it the right length.
Every time. Okay.
Yeah.
I just wanted to double
It's
check.
going to be unhappy with this. Yeah.
And are we allowed to use the math library?
Yes, we're allowed to use any libraries you want. Unless I explicitly say don't in a lab, right? Because sometimes it's useful to make it do things yourself and then use the libraries later. When I was an undergrad, I had my research advisor made us write all of our libraries for MATLAB. We were allowed to use nothing for MATLAB because it was an educational experience. I won't do that to you. Okay. Oh, I should have left some of that. Oh, well. So like I said, you can do multiple ways of implementing the same type of thing. I'm going to look at the clock, sorry. I don't want to go too far into this. There is an example on page 63 of your book that you should probably go through and look at in detail. That talks about the way they actually go through the process of building a full adder, and they go through declaring how to declare the entity, how to declare the ports. They set up the architecture, and then they show that you can do it using mathematic expressions, which I'm going to write those x or y XOR CN, semicolon, and then C out. Do you guys remember full adders from your 2700? With the carry out and everything? I'm kind of assuming you do, but you may need to review that. They use the afters. I don't because they're bad. Well, probably need them for some of the simulations. Anyways, again, we're using the parentheses to ensure order of operations goes correctly. It should anyways. Other times you'll use parentheses just to make it clear, right? Legibility is helped by parentheses. So this is a full adder, right? All I did is write equations. I didn't have to worry about the logic behind it. I didn't have to worry about the gates. I just had to worry about what the expression is for a full adder. When you write, I should go through this. I'm going to do some abbreviation. When you write the architecture, we're going to call this architecture equations of full add is this, right? The this name is arbitrary. That's just you naming it something. The full adder, however, full add, that needs to be the same as the top level entity, right? Because that's how you're making that association. Now, say you've created one adder, right? One full adder. And say it's a 4-bit full adder. You don't want to have to write these equations a whole bunch of times, right? So we're going to have some entity. We're going to call it adder4. It's going to have ports of A, B, and let me just write those down. It's going to have A, B, and CI, or each of these are 4 bits, and the carry is 1 bit. And then we're going to have your outs is just S. Oh, sorry, this is the carry in, this mode. And then I'm going to carry out. 4 bits, again, 1 bit. When I define this or these, because I want it to be 4 bits, I write S is, out. Type is bit vector. And it is 3 down to 0. Down 2 is 1 word. So you're on 3 down to 0. So say I've created the entity using these definitions. I create the architecture, which again I'm going to use shorthand rather than writing it all out. We're going to call it struct of add4, and we're going to now come into and call it, let it know it's now a component using the full adder that we built before. And now we're going to give it some ports. I'm going to switch markers, hopefully find a better one. There we go. Where am I? See out. And obviously we need to know the sum, which are out bits. Close the parentheses, seal the semi, and then we can end component. Now, continuing on from there, I'm going to erase this. Starting a new line going down. I need to define me some signals, connect things together, which is that C. And this one I want to be a bit vector of 3 down to 0. Oops. This one they want to do 3 down to 1. They only want those bits. Oh, because the third one is going to be, sorry, the last one is going to be the carry out. That's why. And now we're going to write the logic for the entity of the add 4. So we've done for the full adder, and we're going to stick 4 of these together, but we don't want to rewrite all of that. So we use what's called port maps. So the first thing that you do is you give it a name. So we're going to start with full adder 0. We tell it it needs the full add that we designed before, port map sorry, I'm going to come back down return. This is comma C at 1 and S at 0. Okay, so now I have a map for how the full adder named FA0 is mapping to the inputs of the upper level module. And I can just keep repeating that if I want to put another full adder into this overall entity. Port, map, and so on and so forth. So I have this 4-bit of A, a 4-bit B, a 4-bit C, and now I'm telling them that the first full adder wants the 0th bit, the second adder wants the first bit, and so on. So I'm just mapping the upper level module down to each of these modules, or sub-modules. Right, so now when I'm drawing my little block diagram that's going between things, is now I have to start considering that I've got a couple little sub-modules inside of that. And you can start cascading those quite a bit. So we call this hierarchical design, right? There's a hierarchy to this. And you can put them all in different files, which is really nice. You can even build whole libraries for yourself in Vhdl like you do in C and Python. Quick term, when we do this and we're giving it a name, just like C, we call that instantiation, right? That's the instance that we're interested in. And of course, I have to end everything, but the book will then walk you through all of the math and show you like how this would simulate. I'm not going to go through that because I really need to push on and get some more material in. It goes into buffer mode, which I talked about, the buffer outs, which I'm not going to cover here right now. Now, if you recall, we talked again previously about sequential logic and combinational logic. Combinational logic reacts to the inputs, right? Sequential logic reacts to a clock. That's your big giveaway usually. So, are we good if I erase this? You recall how I said, if you write this symbol and you have a bunch of statements, they all act at the same time. Well, here's the exception to that rule, is if you call something a process. And you would put sequential statements in here. So you write them the same, but they are going to go one, then the next, then the next, then the next. They're not going to all react at the same time if it's in a process. Now the process needs one more thing, and we call that a sensitivity list, which means it's going to react to whatever is in here. So if you have the AND and OR gate combination before, you want it to react A, B, and D. So you just put A, comma, B, comma, D. And that way, if any of those changed, the process activates and goes through each of those steps sequentially. If you were to say put A and B in there and forget D, then D could change all over the place and it would never react until A or B did. And once it's started, so say A changes, and then halfway through the reaction, B changes, it's not going to restart the process. It's got to finish the process before reactivating. Something that this book does that I like, if you have the book and you look through, for each of these sections that I'm going through, it will actually show you at the end an example of code that will not synthesize for whatever reason. So one of the examples is, look, I built this thing but forgot the sensitivity list, and so it'll show this error. So you can go through and kind of look at those examples of bad code, which is something that I haven't seen in many textbooks and kind of like. If you're trying to use a process to represent combinational logic, so not clocked, it can be very difficult to get it to work. So be careful using processes on combinational logic. Sorry, I'm trying to make sure I get through enough of this, because I do want to have lab 1 on, what is your guys, Wednesday, right? And that is going to require me by Wednesday, the end of lecture Wednesday, getting through state machines in Verilog. So that's why I'm kind of pushing through this really quickly. You'll learn faster once we start getting hands-on and actually start programming things. And the first project, I think, is pretty straightforward. So we should be able to get to that. There is on page 68, it walks through using combinational logic with the process. And it kind of walks through some of the hazards on that. I recommend looking at that. I was going to go through it, I just don't have time. So what you'll often do then, if I'm not doing combinational logic, right, if I'm doing sequential, then I'm going to say process clock. And I will almost always use CLK for the clock, right? And that means every time the clock happens, the sensitivity is going to list. But there's an issue with this, right? Because I said that the process happens every time it changes. So is this positive or negative edge triggered? Both. So that's a little bit of a problem. So what I can do is I can say if clock tick event, so this tick event is part of Vhdl, it's built in, and what it's saying is if something happens to clock, if clock is the thing that triggers this, and that clock is 1. So it's done the process, it looks 1, then Q is equal to D. So this is just a simple flip-flop, right? It's update the output with whatever the input is. This is a process of a flip-flop. This code will probably work. Might have a typo somewhere in there. And event at 1, now it is just positive edge triggered.
And you use the rising edge or clock thing too?
Yes, there is another way to do this. I'm going to walk you through the painful way in the book. And there's kind of a reason for this later on. Did you guys ever discuss, shoot, I forgot the term. I'll remember it. there's an issue. Oh, clock enables. So rather than having the clock, you use the enable to work with the clock. There's timing issues that you can run into if you use just clock. There's another idea that we will use very frequently, especially when you're writing in flip-flops, which is the asynchronous clear. So your flip-flop is going to be synchronous, right? It's going to update on clock edges. But your clear can happen anytime. So I can make the change and say there's now a clear and a clock, and that if clear is happening, sorry, I always do parentheses because I'm used to Verilog. Zero, then Q gets assigned to 0. And actually I should do this, clear N, because you're going to go an active low clear, right, because of that 0. So now I have an asynchronous clear that can happen, and then I can do the else if this, right? I should ask, is there anybody not learned at least one programming language? Okay, good. Because if you haven't learned language, I'm probably going too fast. So I assume that means everybody is happy and comfortable with if-else statements. So I get to skip this whole section. Okay. So I can then start by drawing a block, which we went over. JK flip-flop with a clear and a set. A little bit of overkill, but it works. Sorry, just making sure you guys get a chance to catch up. So we have JK flip-flop. We create entity, JK flip-flop, give it the ports, ins and outs. Didn't write them, save time, and the JK. Now the architecture, shorthand, JK flip-flop 1, this is arbitrary. Differentiate it from JK flip-flop, but this needs to be the same as that, so they're tied together. I start out by saying the signal, Q intermediate, is a bit, and then I'm going to start by saying begin, Q is always assigned to Q int, and Qn is not Q. Now, the reason that I use this Q intermediate is because later in the process, if you look at what the logic is you need, inside the process, you want Q int updating using some of the logic, and then you're going to feed Q int back to the Q, which is the output. So these, you'll notice, are not in the process. So that's combinational, right? Now I'm suddenly in sequential. Combinational is monitoring the sequential, is what's going on here. And then, in the process, if clear, that takes the highest priority, do something. Else if set it. Else if clock, do what a JK flip-flop does on a clock, right? That's all that code is saying. This is how you make a JK flip-flop in shorthand. There's an alternative. I don't like it. If you're, instead of writing a sensitivity list for process, you can, instead of this, you can instead of say wait for, and you can use either a sensitivity list, you can use time expressions, wait 5 nanoseconds, or you can use Boolean expressions like wait for, A to equal B. I guess, sorry, I should probably write that one absolutely correct. In the A equal B, you'd wait until A equals B. And so then you'd execute through, you'd hit this and wait, and you might have some other process doing something with A and B, and it's sitting there watching it and go, oh, now A equals B, move on with the process. And you can put that at the end of the process. And if it's just waiting there and you put a sensitivity list instead of an equality, you end up with exactly the same thing as process as that sensitivity list. So there's 2 ways to write it. I almost always use sensitivity lists. But you could see where the wait until could be useful. I might make this. There's section 2.9. I kind of recommend reading. I highly recommend reading section 2.9. I'm not going to have going through that. It talks about Verilog syntax and scheduling and initialization when it goes into synthesis phase. That kind of talks about some of the nitty gritty. I just do not have time to go. I mean, it's quite a bit of text, but it's not a lot of information. Yeah.
You said it was Verilog?
Sorry, Vhdl. If I say Verilog, I apologize. I have years of experience with Verilog and not as much with Vhdl, and sometimes I slip up. If I start writing Verilog, I also apologize if that ever happens. If you have a model that has multiple processes, which is allowed, all of the processes execute concurrently with each of themselves. So they're all running at the same time. It's not this process, then that process. Each process is its own thing that can happen at the same time. And then that's all stuff that you guys would understand. As someone else brought up, there are Vhdl, I think it was you mentioned, there are Vhdl libraries that expand the abilities of Verilog in very useful ways. But to understand those, we're going to start with some of the basics of Verilog. Not Verilog, Vhdl. Gosh, sorry guys. On page 82 is a list of data types that you can use: bit, Boolean, integer, real, characters, and time. You can also create your own types of data, and the one that you'll use all the time for shorthand, we're going to call it a state type for the moment. The official term is enumerated type. And what that means is all possible combinations of that are defined. Right? Because if you're building a state machine, it's a finite state machine, there's a limited number of states, and you're going to find that and say, my state type is, it's going to be state 1 to 8. And then I can have signals that are assigned to those. And now I can start seeing how we're going to build up a state machine using these types, because I need to step through each of those states. But I'll circle back around to that after I mention on page 82 also, at the bottom is a list of Vhdl operators that you can use, which are AND, OR, NAND, NOR, XOR, right? That's the binary logical operators. Relationship operators, which are equal, not equal, greater than, less than. Shift operators. SLL, SLR. We'll get into what it exactly mean. But anyways, this goes through a list that has 7 different categories, and it shows the order that they execute in. Definitely familiarize yourself with this. It's very important. So things like not execute first. So not A is highest priority, because you're not going to mix that up. The next highest operator is multiplication, right? And it's going to go through all 7 of those in their orders of priority. And one thing to be very aware of, if I write, I cannot do ampersands, don't judge me. This A and B using an ampersand is not 0. It is 1, 0. Ampersand is concatenation. So that's why you write and if you want the logical operator. Page 82 and 83 are really important pages. Just go look at yourself to make sure you're familiar with those. We're down to about a minute, so I'm going to wrap up here. But it's going to go through some shift operators. I'll mark that that's where we are, because those can be a little bit confusing for people. So we'll go through that. I almost made it, guys. I almost made it through everything I needed to. Before we go, does anybody have any questions? Excellent. Good. Thanks for coming, guys. Yeah.
So this is just pure curiosity, so that's why I was asking for the class. But like, for example, if you're using a different language like C or Java, for example, you're using like an array or a string of arrays or vectors or whatever for specific things you want to do, right?
Yeah.
For example, you have bit vectors that are strings that are using Vhdl Design. Why is that?
It doesn't. So we'll get into some more of that.
Okay.
But most of the time, it feels like, most of the time what you're really dealing with is bit vectors.
Okay.
And if you just assume everything is a bit vector and act like that, you're pretty good, as long as you define it that way.
On the last, I did all that.
Like a character, right, is going to be 8 bits if you're asking. And so on and so forth. So you can have but you need to be very careful to define something as integer.
Right.
and then try and do a logical operator on it,
It doesn't like it.
it
Obviously.
does not like it very much. It likes it even less than C does.
Oh, okay, that's fair then.
Well, it likes it about the same as C does, right? Like where C++ will handle that pretty well, right? If you adjusted, if I did the letter code A and it would be fine.
Right.
Because that's 8 bits, that's 8 bits, that's fine.
Right.
Vhdl, it's more questionable if the simulator, well, not the simulator, the synthesizer is going to error or not.
Okay. That's what you're saying. Okay.
And it really is, I know the Altera more, and Altera will actually, you can configure it to be okay with this.
Okay.
But VHDL itself, without the without the IDE, what it's called, right?
Right.
Doing something for you, is not going to be happy. VHDL does not like this because they're different types.
Okay, that's fair. That's what I was curious about because it seemed really open, but then I guess it's just because a lot of it's in bit vector. So
Yes. Yeah.
I was just curious because it's like, as you mentioned, the string that the computer can see just as like a character array, I guess is a way of putting it. And then all of a sudden you were writing vectors, and I was like, oh yeah, like I understand that that's how VHDL works, but I was like, I wonder how it compares and works with all these things because
Yeah,
to
it
me,
can
that's
be
weird.
an issue, and I have to still make sure that I do it correct because Verilog is way more forgiving.
Okay.
And so if I make mistakes, I'm trying to be very clear but there's so much material to cover for this. So I'm trying to be good for you guys. But it's
That's okay. Sweet, that was my question. I appreciate it.
I like the questions. They're good.
So I just wanted to make sure I'm doing this right. For the labs, you want us to just write like our name and the class period?
For Lab 0, that's all I wanted. Lab 1 is going to have some more clear instructions. Don't worry about what's posted right now for Lab 1 because I still have to update it.
Okay.
But for Lab 0, yeah, I just want an image of what I think I listed. I think I wrote it up in the Lab 0 submission.
Okay.
But it is just name, course number, and my signature, and you'll get credit for Lab 0.
Okay, cool. And then for the homework, you just want us to like put it on engineering paper and scan it? Is that kind of what
Yeah.
you're looking for? Cool.
That's what I did. So if that's not right, that's what I put in the submission. I hope this is what you wanted. If it's not, just let me know.
I haven't graded them yet. I'll go through and grade, and if it's wrong, but as long as you're doing reasonable things, it's not going to be bad.
Yeah.
So,
Sweet. I think that was all my questions.
did the homework go smoothly then?
Yeah. The only one that gave me a trip up at first is I think it's 4. It's either 4 or 3, but it's where it gives you. It's the 5K map, but it gives it to you in min terms.
Oh yeah.
And so I just looked in the book because obviously the book's going to tell you how that works. But I got tripped up on when it has the midterm. It's like an E0 M14 or whatever. I was confused at first because I was like, why isn't it just M14? But then it actually does matter because when you look at it that way, instead of putting like 2 1s into the table, you just put a single 1 into the table.
Yeah.
So a lot of it was just like reading to make sure I understood that, but
Okay, good.
Straightforward.
Okay, good. Yeah. Thanks for the feedback. Are you done 1 and 2, or just?
I've looked at 2. I'm doing it later today.
Okay.
Yeah,
Yeah.
it's due Friday, right?
Yeah, I think so. Okay, I'm giving a little bit extra time on each of these. Just
Yeah, because that one has like the Mealy machine I read in it.
Yeah.
And it asks about comparisons with more machines like you've ever class. And then I didn't.
I think that's straightforward. I gutted what Dr. Brown had set up for it because he comes from an old school era where you actually did design using K-maps, because if you have a device that only has 20 gates, simplifying from 20 down to 12 gates is really important. When you have 100,000 gates,
You don't care.
no one cares. Yeah. So
I mean, it's a lot. Well, it depends on how complex your K-map is, because I don't know. You don't want to have like a line of code this long.
No, yeah, you'll do some stuff sometimes, but I've never used a K-map in industry design. I've never done it. So I learned it when I was at your guys' stage of education, and then out the window. But I don't know, it might be useful in some situations in like PhD level ADC design when you're trying to optimize stuff. But, oh, I gotta tell this stuff.
Fair enough. Well, that was my question today. Just out of curiosity.
Oh, and you said we're doing like